So, in part 1 of Unit 1, we talked about fossils, right? Hopefully you know the ins and outs of fossils and you enjoyed some of those pictures and crazy things. But now on to fossil dating. So, not this kind of dating where, the two dinosaurs, they get together and they're like, no, not so much. Fossil dating, we're talking about how do we figure out how old these fossils actually are. So there's a number of things that go into this, okay? A couple of things are, first of all, scientists use two methods to determine the age of fossils. One is called relative dating, and the other one is absolute dating. And read my little comic that I found here. Kind of funny. This old lady, she's a fossil, basically. No, okay, read that. Hopefully you like that. But nonetheless, two different methods. Let's go into those methods a little bit more. So relative dating is a pretty simple thing. Okay, it shows the order in which fossils occurred. So it doesn't give the exact ages. It's kind of like, hey, I think this happened first, and then maybe this happened. Okay, shows what organisms kind of live together. So not to say that relative dating is not important, because it shows different things, but it's not so much this precise exact thing. But it gives us more of a general look as to what was going on during that time period. Okay, scientists look at where fossils are located within the rock. So take, for instance, this picture that I have behind here of the Grand Canyon. You can see where fossils basically were early on, and as the sediments of rocks keep building up, you obviously know that the fossils that were found further down are probably a little bit older, right? And they use the law of superposition. So let's give you a quick little brief introduction to that. The law of superposition, sedimentary layers are deposited in a time sequence. So the oldest rock is on the bottom. Yes, oldest. And the youngest rock is on the top. Right? Brilliant. Hopefully you understand that. So that's the law of superposition, just really simplified. So basically you have the oldest rock that's laid down first, and then these rocks that keep going up with the youngest on the top. Okay? That's kind of how scientists get the relative dating of something. Okay? Now, absolute dating. So the term says it, that basically we're trying to find an exact age for some of these fossils. So it determines that the specific age of a fossil looks at chemical properties of these fossils. There are two types, and we're not going to go into the second one, but carbon-14 I'll talk a little bit about, also known as radiocarbon. So you might hear either one. Potassium argon is another kind of way to determine the age of a fossil as well, but we're not going to talk about that one as much. Okay? So carbon-14 dating, also known as radiocarbon, used to date organic substances. Okay, so carbon-14, anything that's organic contains carbon in it. Okay, so it is going to date organic substances. Scientists measure the radiocarbon in the fossil to determine its age. Okay, can only date specimens up to 60,000 years old. Shucks. No, really, I mean, not to really make a light of that, but 60,000 years old is really not that old considering the age of the Earth. Okay. But anyways, let's look at a diagram that I think kind of helps understand this process a little bit more, okay? So let's take, for instance, we have this particular organism. It's like this little slug kind of whatever, snail-looking thing, right? So living organisms absorb C14, which is radiocarbon, during their lifetime. And I'm going to show you where that stuff comes from in just a minute. But so that's a normal thing. It's like throughout the lifetime they're absorbing this radiocarbon, okay? So then all of a sudden it dies and it becomes a fossil, right? Well, radiocarbon decays at a known rate. We know how it decays and how fast. So basically paleontologists are able to determine the age of a fossil by measuring the amount of C14 it contains. And how they do that is basically they take a small piece of that fossil, they burn it, and it's converted into carbon dioxide gas, okay, when they start to burn that. And from that, you have stable C12 and unstable C14, carbon-14. And carbon-14 decays into N14, emitting an electron and this nitrogen, okay? So then the radiation counter can kind of basically record the number of electrons emitted, and that can tell the actual age of something. So it's kind of crazy that you take all these different parts, from radioactive decaying to, doing this and that and this and that, only to find how many electrons are emitted, and that's going to tell you the age. So it's kind of interesting to think about that. So that's what happens in carbon-14 dating, okay? Now, like I said, you're like, where did carbon-14 come from? I don't get it. You say that these organisms are just absorbing it. Yeah, right. Well, when you think about it, here's our Earth. There are cosmic rays constantly bombarding the upper atmosphere, okay? These cosmic rays produce fast-moving neutrons. Remember, neutrons have a neutral charge. They're found in the nucleus, okay? So very fast-moving neutrons. And the neutrons are going to collide with these atmospheric nitrogen atoms because there's nitrogen in the atmosphere, okay? Along with oxygen, along with some other things. So it's going to collide with this nitrogen, and it produces the radioactive carbon-14, okay? That is basically in the atmosphere. So just like that said, that basically that fossil was absorbing it through its lifetime, and therefore you can, those paleontologists and different scientists can actually figure out how old those fossils are. Right? All right, so radioactive decay. And I love that term because it just makes me think of crazy mutant things like this picture. So radioactive decay, the nuclei of some chemical elements. Remember, the nucleus is the protons and the neutrons in the center of an atom, okay? Well, some of those are unstable and against the strong nuclear force holding them together. So sometimes if they're unstable, it's going to result in a spontaneous change of characteristic or identity of the element. So basically, it's going to completely change that element because of the instability, okay? This is especially common for those elements that are above 92 in the periodic table, 92 being the atomic number, okay? So anything above 92 is very radioactive. It's very unstable, so it starts to kind of change with kind of its characteristics, okay? There are 3 methods of decay. We're not going to really go into those, but just know that there are different types of decay, and the decay process releases energy that can be measured. So basically, I am just kind of explaining that same process again in a little bit different manner. So basically, that decay process, the energy that's being released are those electrons that are emitted, and those radioactive whatever, they can detect how much is being emitted, and so that's in the form of energy, okay? So a little bit more on radioactive decay. And if you guys don't understand that concept, because it is a hard one, I feel like I didn't quite understand it until I was like done with college, and I was like, aha, I get it. Good thing I'm not taking any more of those classes and I can't really actually pass a test. No, just kidding. I'm going to get you to pass a test on this, but I'm not going to I'm not going to test you too heavily on that, but understand a little bit about radioactive decay. So half-life, again, I want you to know this term, but I'm not going to have you calculate stuff. But I want you to understand what half-life is. It's abbreviated T and then this little subscript, 1/2, okay? It's the period of time that it takes for the amount of a substance undergoing decay to decrease by half. That's it. Understand that definition. That basically when we're talking about that, radioactive decay, we're talking about the half-life is the period of time it takes for the amount of whatever substance you're figuring out, how old it is, to undergo decay and decrease by half. Okay? So when you kind of break it up, that basically the half-life is talking about how much time does it take for that substance to basically decrease its mass by half. Okay? By measuring the amounts of different isotopes in a sample, geologists can calculate the age of the sample. Okay? So the half-life has to do a little bit more with mass rather than how much energy is emitted once it undergoes, when you heat it up, okay? All right, so there's half-life for you. All right, here's the last thing we're going to talk about in part 2, geologic timescale. We're going to look at something in just a second, but I want you to think about this question. Now, obviously, I'm speaking to you, and you can't really talk back to me, although you can. I just won't answer you. But what is old to you? I mean, when you think of old, you're like, yeah, my grandma's really old, or like I used to go to a nursing home to visit my grandma, and I'm like, whoa, these people are old. But, okay, these are the people I think of when I think of old. Okay, I found these, of course, on Google, and I'm like, whoa, that dude looks old, right? This poor woman probably can't see and definitely can't chew because she probably has no teeth. But I hope I am as happy as these people, the hipsters, total hippies that are, age 80 or something. And then this chick, she is having a grand old time dancing. This guy, I don't know, maybe one of those grumpy old men. But nonetheless, sometimes I think of, yeah, that's old. But not really when you think about the age of the Earth. 4.5 billion years old. How about that? Is that old to you? I can't even fathom that. Okay, that's the estimated age of our Earth, right? So there's still differences among some scientists and among different people, but that is what it's been calculated. Okay, so I can't even imagine that. I say, holy cow, craziness, 4.5 billion years. So in the next couple weeks, just so you guys know, we're going to be going through 4.5 billion years. We're going to talk about what started it and all the way through until present time. Kind of crazy. So not too long, we'll be going through everything. So the first geologic timescale was proposed in 1913 by the British geologist Arthur Holmes. Okay, he died in 1965, but he's basically the one that came up with that first geologic timescale. What happened throughout time, throughout these 4.5 billion years ago? Okay, so I'm going to show you guys in your actual course. You have a really good picture of that. Okay, and here is, and you're not going to be able to see a ton of it. But I want you guys, I'm going to bring this over just a little bit so you can see a little bit. And this is actually what you'll find. I didn't want to do that. This is what you'll find when you click on a link in your course. Okay, and it'll say on the very last page of section 1, it'll say click here for more information on this. Well, it brings up a great geologic timescale. And again, you're not going to be able to see a whole lot of this because the screen for recording isn't quite that big. But as you notice, and we'll come back to this in the next couple weeks, when we talk about, I shouldn't say the next couple weeks, the next week and a half is when we're going over this stuff. But you can see that it talks about all of these different time periods. Okay, we're going to go over these. The Cenozoic, and then you have, it breaks it down into even smaller, basically, periods. The Mesozoic time period, down here the Paleozoic. You have the Proterozoic and the Archean, and then down here the Hadean. Okay, we'll start talking about the Precambrian era next. But really, it's really cool to look at these geologic timescales and really see that, holy cow, there is so much that is put into this. Sorry, I could have moved that over a little bit more. Okay, so please go through. The cool thing is you can click on, say you want to look on the Ordovician. And you're like, what the heck happened to the Ordovician? And you click on it, and then it gives you a whole bunch of information just on the Ordovician time period. Okay, so it's pretty cool. You can go down, you can find pictures. So I really, really encourage you guys to take a look at some of this stuff here that you're going to find in the geologic timescale and look at that. Okay, so anyways, that is about it. I want you guys to make sure you get familiar with that geologic timescale because we're going to be going through it in depth. All right, so alrighty then, calling it quits. We'll see you for section 2.